Hello, statistics class. I'm going to go over chapter 4, section 4, part 4, the last part of this chapter. Sorry, of this section, not of the chapter, but of chapter 4, section 4, the last part of that. There's a section 5 for chapter 4. And this set of notes is on checking for independence. Okay, so in the last section, we discussed what it means to be independent and how to find the conditional probability of two dependent events where the outcome of one event affects the outcome of the next event. We use this symbol to indicate given, so probability of B given that A occurred. And then at the very end of that section, we looked at probability of independent events, where the probability of events that do not affect each other, you just multiply. Okay, so the way you can check for independence is if the probability of the intersection of A and B is equal to the probability of A times probability of B. So, for instance, if you're flipping two coins and you want heads on both of them, okay, so you want heads on the first coin and heads on the second coin. The probability of both of those occurring is 1/2 times 1/2. Okay, so the probability of them occurring independently is 1/2, right? So for each of them, so it would be 1/4. Okay, as opposed to if let's say a different option or a different situation would be as if you had 10 balls in a basket and 2 of them are red. That's kind of like the example we had. I don't know if the numbers are exactly right, but if you pull one from the basket, and you're asking what are the chances I get a red ball? Well, if I'm pulling a ball out, there's a 2 in 10 or a 1/5 chance that I get a red ball. Okay. Well, if I pull a second ball out, I will have, if I already had a red ball pulled out, okay, well, that changes the number of balls in the basket. Okay, so doing that twice would be 2/10 the first time, but it won't be 2/10 the second time. So 2/10 times 2/10 would not match what the intersection is. Okay, that's how you can check for independence. So where 1/2 times 1/2 is equal to 1/4, that works. 1/5 plus 1 times 1/5 would not equal the intersection, because the intersection will actually be more complicated than that. It won't end up being 1/25. Another way you can test for independence is if the probability of B given A is simply B. So the probability of B given A, the given A doesn't affect the outcome of probability of B. So in the coin toss scenario, probability of B given A, the probability that you get a heads on the second coin, given that you got a heads on the first coin, is still going to just be 1/2. But in the pulling a ball out of a basket situation, the probability of the second red is going to be 1/9 and not 1/5, 2/10 any longer. I don't know if that made sense, but the thing is that we need to be able to test for independence given some statistics. So let's look at some examples, and if that didn't make sense, hopefully these examples help. We're tossing 2 coins. The whole sample space of tossing 2 coins will be heads heads, heads tails, tails heads, tails tails. There's four possibilities for tossing 2 coins. So the probability of getting heads on the first coin will be 1/2. The probability of getting tails on the second coin, we're going to label that B. Heads on the first coin is A. Tails on the second coin is B. The probability of both of those are going to end up being 1/2. 1/2 for the first, 1/2 for the second. So this will be very much like I was verbally saying, and you can see it right now. So to test whether or not these are independent events, we're going to find the probability of the intersection of A and B. Okay, the probability of A and B. So one of these is that scenario. We have 4 scenarios. They're equally likely. Heads, tails is 1/4 of one of the 4 scenarios of getting A and B. Okay. the probability of A times B is, so we know that the probability of A is 1/2, and we know that the probability of B is 1/2. Okay, so the probability of A times B is 1/2 times 1/2, which is 1/4. These are equal. Okay, they are independent events. They do not affect the outcome of the one event, does not affect the outcome of the other. Okay, because 1/4 is equal to 1/4. 1/4 is equal to 1/2 times 1/2. Hopefully that makes sense. Okay, here's a table of probability table of, this is probably table that we looked at before in a previous example, of people surveyed about whether or not they think college is too expensive, and whether or not, and it also indicated whether or not they had children in college, and what they thought about college. Okay, so the question is, are events D and A independent? Events D and A. D is the number or the percent of people who have children in college out of the people surveyed. A is the percentage of people who thought tuition was too high. Okay, so probability of D would be the sum of 35 plus 8 plus 1. So you just go across here to find all of the total for the children in college. Okay, so 44% of the people surveyed had children in college. Probability of A, that is the number of people who thought the college was too high. You have to add the total of this column is 60. Okay, so to find the probability, if these two events are independent, we want to find the intersection of those, which we can do by looking at this spot that they share, the 35. Is that equal to the product of A and D? We take one on your calculator. You can take 0.44 times 0.6, and you get 264. That is not equal to 35. These are dependent events. That having a child in college does affect whether or not they think, in this survey, but it does affect whether or not they think college is too expensive. There were two different ways to check independence at the beginning of these notes. We had whether or not the product of the events individually is the same as the intersection of the events. We also had the probability of B given A is equal to the probability of B. So that means the probability of B given A is the same as the probability of B not, whether or not A is given, which means given A had no effect on the probability. Okay, that's the second way of testing this. So let's look at that. So the probability of D is 44. We looked at that already. We found that already. Probability of A is 60. We looked at that. Okay. Probability of the intersection is 35. Is the probability of A given D the same as the probability of A? That's what we're going to look for here. Probability of A given D equal to the probability of A. And if it is, they're independent. We already know that this is dependent, so we know this is not going to be equal, but it's just another way to do it if we did not do it already. Okay. The intersection of A over D, the intersection of A intersect D is 0.35. We're going to divide that by the probability of D using the given formula that we learned in the last chapter. This is the formula for the probability of A given D is equal to the, and it's equal to probability of the intersection of A and D over the probability of D. So 0.35 divided by 0.44, which is a 70, almost 70, or almost 80% chance. And is that equal to the probability of A by itself? No, it is not. Okay, so either way, it didn't specify which way you need to use, which method you need to use to check for independence. So either way would work. Okay. 2 cards are drawn from a deck of 52 cards. Calculate the probability that draw includes an ace or a 10. Okay, so we're going to calculate the probability that an ace or a 10 is drawn. A, we're going to call A the event that an ace is drawn, and B the event that a 10 is drawn. Okay, so if you pull A, you have a 4 in For A, you have a 4 in 52 chance of pulling an ace, because there's 4 aces in a deck. There's a 4 in 52 chance of pulling a 10, because there's 4 10s in a deck. However, the probability of the second draw is going to be different because of the fact that if you want to draw a 10 on the second hand, there's only 51 cards left. Once you draw an ace, you have one less card in that hand. But there's still 10. If I drew an ace, there's still going to be 4 10s left. So the probability of a 10 given an ace is 51, and the probability on this side, if you already pulled a 10, the probability of an ace is 4 out of 51 because the ace is gone, so there's one less card, but there's still 4 aces. Sorry, the 10 is gone. There's still 4 aces. So it doesn't matter which way you go, whether you pull the 10 first and then the ace, or the ace and then the 10. So we're going to actually have to do a sum here of these two probabilities. Pull in an ace and then a 10, and then also the probability of a 10 and then an ace. But we need to multiply the dependent events together to find the probability for each of those different scenarios: ace and then 10, and 10 and an ace. Okay, so the probability of an ace and then a 10 would be 4 over 52 times 4 over 51. 4 chances on the first, 4 chances on, I'm sorry, 4 out of 52 on the first, and 4 out of 51 on the second. So both of those parts of this, because it's 4 out of 52 times 4 out of 51 for both, is 16 out of 2652. You add those together. Common denominator already, 32. Simplified, it's 8 out of a 663 chance. So there's going to be a 1.2% chance that you can get an ace and a 10 out of a deck of cards. Okay. All right. So there's 5 problems for you in the bookwork. Again, I'll post that PDF so that you guys can see the problems. Hopefully it's made sense. And I wasn't too unclear about this, but as always, please ask questions. Thank you, and good day.